Hello everyone. In this session, we are going to think about a transistor common emitter characteristics. At the end of this session, students will be able to describe transistor common emitter voltage current, that is VI characteristics. These are the contents of this session. Now let us first think about what is a common emitter circuit configuration. In common emitter circuit configuration, the input signal that is to be amplified, that is applied to the base terminal of transistor, and output is taken from the collector. The emitter terminal is common to both input and output. Now let us consider the circuit diagram. Now this figure shows the circuit diagram for a transistor connected in common emitter circuit configuration. So in addition to biasing voltages VBB and VCC, VBB is DC voltage that is used to forward bias base emitter junction. Usually base emitter junction is forward biased and collector base junction is reverse biased using external DC voltage plus VCC. Consider NPN transistor. So in addition to these biasing voltages, the input AC signal, that is a low amplitude, small amplitude input AC signal that is to be amplified, is applied to the base of a transistor with respect to emitter. And the amplified output signal, the amplified output voltage and current is taken from a collector. So emitter is connected, remains connected with the common point in the circuit that is common to both input and output. So this is what the common emitter circuit configuration for a transistor. The input current for a transistor is base current IB, that is resulting due to input AC voltage signal Vin, and the input voltage, effective input voltage for a transistor, that is the amplifying device, the voltage between base and emitter. Voltage at base with respect to emitter. Emitter is connected to ground. It is grounded. It is common to both input and output. So voltage VB, base to emitter voltage, is the effective actual input voltage for a transistor. And the voltage taken from collector with respect to emitter, so that is designated as VC. So that is the output voltage of a transistor. And current flowing in the collector terminal, that is the collector current. So collector current is the output current of a transistor. So IC is the output current and VC is the output voltage, and VB is the input voltage and IB is the input current. And the resistance connected in collector terminal, either it is a collector resistor RC or a load resistor RL. So that is the current limiting resistor connected in collector terminal. It limits the amount of collector current as well as it is used to produce the output voltage. Now let us go for the voltage current characteristic of a transistor in common emitter circuit configuration. It is nothing but the response of transistor for a variation of input voltage and input current for certain fixed value of output voltage. And in another part, in another way, the variation of the response of transistor for a variation of output current and output voltage for constant input. So first let us go for the input characteristic of a transistor in common emitter circuit configuration. So input characteristic of a transistor in common emitter circuit configuration is a graph of input current IB versus input voltage VB at certain constant value of collector to emitter voltage. So this figure shows the graph of IB versus VB at certain constant value of collector to emitter voltage. So there are two graphs, two curves considering two different values, two different constant values for collector to emitter voltage. So from this graph, it is seen that as base emitter voltage is increased from origin 0 value, initially as long as voltage at base with respect to emitter is less than or below the cut-in voltage of a transistor, so that is about 0.7 or 0.6 volt for a silicon transistor and 0.2 to 0.3 volt for a germanium transistor, the current flowing in the base terminal is very small. So that is approximately 0. So transistor does not conduct, base emitter junction is not forward biased. When base emitter voltage just exceeds the cut-in voltage of transistor, base emitter junction is forward biased, and after that there is a sudden increase in base current IB. IB increases rapidly, sharply, with further increase in base to emitter voltage. Once base emitter junction is forward biased and cut-in voltage is overcome, cut-in voltage is exceeds. So from this graph, it is seen that for small increase in base to emitter voltage, there is large change in base current IB. So from this input characteristics, we can obtain the input resistance of a transistor. So considering the change in base to emitter voltage and corresponding change in base current IB, we can find out the dynamic input resistance, that is the AC input resistance of transistor in common emitter circuit configuration. So that is given by Rn equal to input resistance delta VB change in base to emitter voltage divided by delta IB change in input base current IB at certain constant value of collector to emitter voltage, output voltage. So relatively, as compared to common base circuit configuration, the input resistance of a transistor in common emitter circuit configuration is higher. So input resistance of transistor in common emitter circuit configuration is at medium level because the base current IB is in terms of microamperes, So the input resistance of transistor in common emitter circuit configuration is medium. As now from these two graphs, it is seen that as collector to emitter voltage is increased, there is a slight decrease in base current IB. For a given value of base to emitter voltage. Considering certain constant value of base to emitter voltage, as collector to emitter voltage is increased, there is slight decrease in base current IB. So this is due to this happens due to early effect. So this is about the input characteristic of a transistor in common emitter circuit configuration. Now let us go for the output characteristic of transistor in common emitter circuit configuration. In common emitter circuit configuration, the output characteristic is a graph of output collector current IC versus the output collector to emitter voltage VCB at constant input base current IB. So in active region, the collector current IC varies linearly with the input base current IB. In active region, both collector base junction remains reverse biased and base emitter junction remains forward biased. The operation of transistor is linear. The output collector current is directly proportional to the input base current IB. As IB increases or decreases, corresponding to that, the IC increases and decreases. So whenever transistor is operated as amplifier, it is always operated in active region. In saturation region, the voltage across transistor between collector and base is collector and emitter is minimum, and the collector current IC rises to maximum possible value, that is saturation value for a given value of input base current IB. So that is the saturation region. In cutoff region, both junctions of transistor remains reverse biased, so transistor does not conduct. So the region below IB equal to 0, that is the cutoff region for transistor. In this region, transistor remains off. As far as the saturation region is concerned, in saturation region, both collector base junction and base emitter junction remains forward biased because voltage at emitter is at lower potential. Voltage at emitter is at lower level with respect to voltage at base in saturation region. So this is about the output characteristic of transistor in common emitter circuit configuration. In active region, IC slightly increases with large increase in collector to emitter voltage. So as collector to emitter voltage is increased, IC slightly increases. And actually the IC is independent of collector to emitter voltage. It depends upon the input base current IB. But there is slight increase in collector current IC with increase in collector to emitter voltage. So this, from this output characteristics, we can get the AC in output resistance, that is dynamic output resistance of transistor designated as RO. So that is given by delta VC, change in collector to emitter voltage, divided by change in collector current IC at certain constant value of input base current IB. For a large increase in collector to emitter voltage, there is slight increase in collector current IC. So output resistance of transistor in common emitter circuit configuration is very high. The DC current gain of transistor in common emitter circuit configuration is defined as designated as beta equal to the ratio of output collector current IC to the input base current IB. So IB is in terms of microampere generally, and IC is in terms of milliampere. So value of beta is very large. So IC is much larger than IB. So beta value is always higher value. And AC current gain of transistor, same transistor, beta, again it is a ratio of change in collector current to change in base current IB. So practically the value of DC current gain and AC current gain are approximately equal for the transistor. The voltage gain of transistor in common emitter circuit configuration, it is given by AV equal to ratio of output collector to emitter voltage to input base to emitter voltage. So collector to emitter voltage is larger, much larger than base to emitter voltage. So the transistor provides voltage gain in common emitter circuit configuration. Now student can pause video here and think over this question, try to answer this question. Why does slightly IC increases and IB decreases with an increase in VC? The answer is, this is due to the early effect. As reverse voltage at collector is increased, the width of depletion region at collector base junction increases. So effective electrical width of base region decreases. So charge gradient in a base region increases. So relatively some more number of minority charge carriers are injected from emitter region to base region. So due to that, there is slight increase in emitter current, and correspondingly the collector current IC also increases, and there are less recombination of holes and electrons in base region, so IB slightly decreases. So this is the reference. Thank you.